The image you provided is a question from a pharmacist's examination that took place in May 2010. The question asks about the importance of a drug's half-life. Half-life is the time it takes for the concentration of a drug to decrease by half in the bloodstream. It's a crucial factor in determining how often a drug needs to be administered. The options provided and their answers are as follows. A. Dosing frequency. True. Half-life is directly related to dosing frequency. Drugs with shorter half-lives need to be administered more frequently, while those with longer half-lives can be taken less often. B. Extent of bioavailability. False. Bioavailability refers to the amount of a drug that is absorbed into the bloodstream. While half-life can influence how long a drug remains in the body, it doesn't directly affect its absorption. C. Time to reach steady state. True. Steady state is the point at which the rate of drug elimination from the body equals the rate of drug administration. The half-life determines how long it takes to reach steady state. D. Time taken for elimination from the body. True. The half-life is an indicator of how long a drug takes to be eliminated from the body. A longer half-life means the drug stays in the body for a longer time. E. Time taken for the concentration of the drug to fail by 50%. True. This is the definition of half-life. In summary, the half-life of a drug is important in determining the dosing frequency, time to reach steady state, and time taken for elimination from the body. It does not directly affect the extent of bioavailability. Half-life refers to the time it takes for the concentration of a drug in the bloodstream, plasma, to decrease by half. Here's a breakdown of the key points. Half-life, the time required for the drug concentration to be reduced by half. Plasma concentration, the amount of the drug in the bloodstream. Drug elimination, the removal of the drug from the body. Distribution, the movement of the drug to other body fluids and tissues. Clearance, the rate at which a drug is removed from the plasma. Volume of distribution, the amount of space a drug occupies in the body. The half-life of a drug is influenced by both clearance and volume of distribution. A drug with a shorter half-life is eliminated from the body more quickly, while a drug with a longer half-life stays in the body for a longer period. The formula for calculating half-life is T1/2 equals 0.693 *VD, Cl, where T1/2 is the half-life. 0.693 is a constant. Vd is the volume of distribution. Cl is the clearance. This formula helps determine how often a drug needs to be administered to maintain a therapeutic concentration in the bloodstream. The text discusses the concept of half-life in pharmacology. It explains how half-life is influenced by the volume of distribution, Vd, and clearance of a drug. A longer half-life means the drug stays in the body longer, while a shorter half-life means it is eliminated more quickly. The half-life is important because it helps determine the dosing frequency of a drug. Drugs with a short half-life need to be administered more frequently, while drugs with a longer half-life can be taken less often. The therapeutic index, TI, of a drug also plays a role in determining dosing frequency. The text discusses the concept of half-life in pharmacology, focusing on its role in predicting the time to reach steady state and estimating drug elimination in cases of poisoning or overdose. Steady state is the point at which the rate of drug absorption equals the rate of drug elimination. It is typically achieved after 4 to 5 half-lives of a drug. For drugs with a very long half-life, reaching steady state can take several days. In such cases, a loading dose may be used to quickly achieve the desired plasma concentration, followed by a regular maintenance dose. The size of the loading dose depends on the volume of distribution. In cases of poisoning or overdose, the half-life can be used to estimate how long it will take for the drug to be completely eliminated from the body. Factors that can affect half-life include physiological states and disease conditions. These can influence the volume of distribution and clearance, which in turn affect half-life. Examples include newborn and old age, pregnancy, and hepatic or renal impairment.